Okay, so now we're back again, and we want to continue the story. Well, this pinhole is actually the place from which we view the image, or the positive image, so we're going to call that the viewpoint. I'm going to open that. And we're going to call that the viewpoint vector, and we're going to give it generic coordinates because we want to be able to move the camera around. That's when you take pictures, you move around to try and find the best place to view the object from. So the next thing we need to define, having placed the camera somewhere, is to point it at the object, and it's got the wrong one. And we're going to call that the normal vector, or the camera axis vector, and we're going to define it as a unit vector in terms of spherical polar coordinates, and these are completely analogous. Theta is analogous to the polar angle or latitude of a point on, for example, on face of the Earth, and phi is the azimuthal angle or the longitude in geographical terms. And we can check, we better execute or establish the viewpoint vector, and then we want to establish the normal or the camera axis vector, and check that it's actually a unit vector by working out its the square of its length by taking the scalar product of it with itself, which is 1. So we now want to define the remaining 2 camera axis vectors. Well, normally when you use a camera, you usually have one of the axes of the camera horizontal. If you don't, it looks kind of funny. So I'm going to choose that horizontal screen axis vector to be this. In other words, defined in terms of the azimuthal angle phi, and I can check that that's actually perpendicular to the camera axis vector using that. In other words, the scalar product of that with the camera axis vector is 0. So now I've got 2 vectors in the camera frame of reference, and we want to find the third. Well, if the first screen vector is horizontal, then the other one must have a vertical component so it must have a non-zero vertical or z component. And there are 2 ways of finding this vector: the Gram-Schmidt algorithm and the vector product. And we will compute this vector using both methods. So let's start with Gram-Schmidt. So we define the third, the vertical screen axis vector to be a unit vector in the vertical direction, and then a linear combination of the camera axis vector and the horizontal screen axis vector. So we define that, and then we're going to require that vector be perpendicular to both the camera axis vector and the horizontal screen axis vector. So we take the scalar product, we get an equation by taking the scalar product of this vector with the camera axis vector. And we can see that only involves the parameter alpha, and that in fact alpha, we set that equal to 0 and solve for alpha using this, and we find alpha is minus sine theta. We can get another equation by requiring that this vector be perpendicular to the horizontal screen axis vector. So we get another equation for beta, and that's a very simple equation because it implies that beta must be 0. We can find that. I should say that when I work in Mathematica, then all my equations, I have the convention that all my equations are of the form something equals 0, and that means that I don't have to carry the equals around, and I can multiply the equations by whatever I like. So now I've got that, and I'm going to put those solutions into my expression for the vertical screen axis vector, like so. And now I need to have make this have unit length, so I'm going to calculate the square root of, or if you like, the length of that vector on the assumption that cos theta is greater than 0. Well, theta is an angle between minus 90 and plus 90 degrees, or minus pi over 2 and plus pi over 2. So I simplify that with the constraint that that be positive, and that finds the length of the vector, and so I can divide by that length, and that gives me this expression here for the vertical screen axis vector. The other way of doing it is just by taking the vector product of the horizontal screen axis vector with the camera axis vector using this, and we can see that that gives exactly the same answer as the Gram-Schmidt method. So these two vectors u and w that we've just found provide an orthonormal basis for the subset of subspace of points where the lines from the viewpoint to the image points cut the screen plane. So I think we'll stop there and